In question number 4, a progressive longitudinal wave travels through a medium. Okay, actually, the meaning of this progressive now is we studied two types, or we can say that two categories of wave. One is the standing, and second one is the progressive. Progressive waves are the normal waves that we studied in our first chapter of waves, right? And in the second chapter of superposition, there is a concept of standing or stationary waves, right? So that's why now they are using the concept and the term progressive waves. So they may make clear that either we are talking about progressive or standing waves, right? Okay, so the question is traveling through a medium from left to right. Figure 4.1 shows the position of the sum of the particles of the medium at time t is equals to 0, and graph showing the particle displacement at same time t naught. Direction of travel is also given over there. And what we need to do in this question, okay, the first part is particle displacement to the right of their equilibrium position and particle displacement to the left are shown as negative on the graph. Okay, the period of the wave is t. On figure 4.1, draw circles around two particles. So this is our main concern in this question. Draw circles around two particles which are exactly one wavelength apart. Okay, so this is our first scenario to find out one wavelength apart, and we need to mark two circles that will give you the concept of one complete wavelength, right? So what we need to do, and you can see that when waves are close to each other, particles are close to each other, so that gives you the concept of compression, and when they are away from each other, so they gives you the concept of rarefaction, right? But the question is something different. We need to find out exactly one wavelength apart. Okay, recently we discussed about the concept of phase difference, right? Uh, Here it is, right?
Yeah.
What we did, we just choose a starting point and then we complete the one wavelength and just find the distance. So we may use this concept also in our question to find out the distance between 2 points that is equals to one wavelength. So actually, let's suppose if we consider the first point, let's suppose we circle our initial first point. So what will be the next point that we need to mark? This one,
Yeah. So that's one wavelength.
one wavelength. Simple.
Like that's
Yes. Now you simply got the concept. How many dots are there in between 2 points? Three, four, 7 dots, right? So now it makes very simple. Let's suppose if you mark the second one, so it will be at this point. So that will give you the concept of this one. So second point will be this. Now again, 7 dots between these two blue circled marks, right? So this is our first part. You may choose any one, either red or either blue, but you only need to mark only one distance. So this is our first part.
yeah, okay.
And in second part on figure 4.1, sketch a line on the graph to represent the displacements of the particle. So we need to sketch on a graph to represent the displacement of the particles for the longitudinal wave at time t is equals t naught plus t over 4. So this is something different. You need to sketch
Yeah.
and you need to mark, or we can say that we need to add new line on a graph that will show you the displacement of particle for longitudinal wave at time t naught is equal plus t over 4. T over 4, we already discussed that concept in our last topic in standing wave. When we are calculating the length and the wavelength from the standing wave, that will be equal to 2 lambda sometime lambda 5 4. So that concept we can just relate over here, because let's suppose if we mark points on the wave, something like this, that this is a complete crust of one wave, this is the complete trough of the first wave, then this is again the complete crust of first wave, and this is the complete trough of uh, second wave, right? So if we consider our first wave, because we are getting one wave over here, So this is our first wave. So if we consider first wave in initial condition, and if we split this wave into half, like we just draw a mark over here, and we again draw a mark in the middle of the truck of first wave. So now you can see that our complete wave is split up into four parts, right? And we need to start from which time? T naught plus T by 4. Okay. T naught plus T by 4 means this is our first, second, third, fourth, right? So we completely divide wave into four components, right? So T over 4 means we need to select that time which is 1/4 of the complete wave. Are you getting the concept?
Yeah.
So we need to select this point, right? Because at this specific point, we are getting time T by 4. Because this is our first part, or we can say
Yeah.
the 1/4 of the total wave, right? So actually what we need to do, we need to start from this
Yes.
and just simply mark perpendicular points over here at this one. And the next will be, this one will be minimum. This one will be maximum, and again we are going to have maximum and then minimum point. So our new wave will be like this. Let's make it with red color. So this red wave shows you what, that this initial time is t naught, and we just simply add the t4. So our initial position was displaced from 0 to point, right?
Right. So it's the same amplitude, but it just starts from a different point.
Yes, so we need to only represent this important point, that time will be t naught plus t by 4. Amplitude will remain same because they mention which are to represent the displacement. So their main concern is to represent the displacement. Okay, so they are not asking about the amplitude or any other change in the wave, right? So this question is of 3 mark, right? So if you got the concept right, so you will get 3 mark very quickly in this question, right?
Yeah.
Okay, so this is our third part. Now move towards, sorry, this is our now third part. So in third part, what we need to do, state the direction of motion of particle Z at time t naught plus t by 4. So actually what we need to do,
Uh,
we need to first find particle Z. So this is particle Z, right?
okay.
And you need to mark what actually they are asking about. State the direction of the motion of the particle of Z at time t naught plus t by 4. If we complete this wave throughout the complete timeline, so it will be maximum over here, then minimum at minimum, it is completely minimum at the center. So at this point, it will be minimum. Okay, so this is the complete motion of the wave throughout the experiment. So they are about this point Z. So actually, we need to define the state the direction of the motion of particle Z. So actually, we know that this red wave is moving in the forward direction, and all waves, or we can say that this red wave is also a progressive wave. So we can easily mark, because it is mentioned in the second part, the longitudinal wave. So according to the concept of longitudinal wave, this particle Z will move in which direction? Forward or backward?
Then move forward.
Forward, because we are talking about longitudinal wave, and according to longitudinal wave, red wave is also progressive, and we simply observe that the direction of wave is also in forward direction. So this red line will also move towards right hand side. So the answer of this question is very simple, to the right. And part B, the frequency of the wave in part A is 16 kilohertz. This is our frequency. And the distance between particle X,
Okay.
yes,
Is that the wavelength? The X and Y?
the frequency between points. X, Y basically are just 2 points. They are talking about these 2 points. And
So
this,
it's X and Y. They're half a wavelength,
yes, yes,
right?
yes,
So then to have a full wavelength, it's gonna be times 2. So it's you're gonna get
yes,
0.6, I think.
yes, nice. So you already got the
Yeah,
concept.
38, 0.38.
Yes. So you need to multiply by
It's
2.
0.38 meters, and then the 16 kilohertz. Yeah, and then the 16 kilohertz is 16,000 hertz. So then what you're gonna do to find the speed is you're gonna multiply the 16,000 by the 0.38, and you're gonna get 6,080, but then you're gonna round it to 2 decimal places, so you're gonna get 6,100. Not decimal places, but significant figures.
Okay, very good.
Yeah.
So your frequency is 16,000 and your wavelength is 0.38. You here by yourself.
Yeah, I got 6,080, but then you have to round it to 6,100.
Okay. So 6,100. This is your final answer.
Yes.
Okay. Okay, so this is not very difficult. Only there is a trick in this part, that you need to identify correct wavelength. So that is only an important concept in this question in part B. Otherwise, remaining question is not a very difficult one. Now part C is related to intensity. A longitudinal sound wave is traveling through a solid. The initial intensity of wave is I naught, and the frequency of wave remains constant. Okay, so frequency is constant, and the amplitude falls to half. Okay, so amplitude falls to half of its original value. Determine in terms of I naught the final intensity of the wave. So you need to find out the final intensity. So actually, what we need to do, we know that intensity is directly proportional to the amplitude square, right?
Yeah.
And now we are talking about the intensity initial and final stage, right? So whenever the question will be like this, that determine in terms of intensity, or find out the final intensity, or compare the initial and final intensity. So whenever you got question like this, so always use ratio method or comparison method like this. Let's suppose if we consider initial velocity as I naught over a naught square, this is our initial, right? Is equals to what? I over, or we just write I2 over A2 square, right? So this left hand side represents you the initial form, and the right hand gives you the of the final form, right? And why we are in the value, let's say if you take the reference from this equation number one, if we just shift on the left hand side, so it will be definitely equal to some value. So that's why we use the ratio method and the comparison method by writing two ratios, one on the left and second one on the right. Okay.
Okay.
Now what we need to do, we got the concept from the question that amplitude is half, falls to half from its original value. So we just simply proceed by the steps like I naught over a square is equals to I2 over half of the original amplitude. So your amplitude will be half square, right? So now you just need to do some mathematical step that will give you the final answer. We need to find out the value of I2. So I2 will be equal to what? I2 is equals to this 2 will become 4, right? And it is going to be multiply on the other side. So it will be equal to A naught square over 4 multiply by I naught over A naught. This whole component is add on the left hand side. Okay. Any confusion?
No.
Okay. So now you just need to cancel out the values. You know that this whole amplitude is going to be cancelled out. Okay, square is missing over here because square is here also. So this quantity is going to be cancelled out. So it means that your final intensity will be 1/4 of your initial intensity, right? Your initial intensity is 0.25 of your initial, right? They already mentioned I naught. Okay. The next part is the sound wave in C now meets another wave traveling in the opposite direction. State a necessary condition for these two waves to form a stationary wave. That we recently discussed in our topic of the coherence, that is very necessary to form a stationary wave, and that we already discussed in our standing wave parts. If you remember that we studied about the monochromatic concept, and yes, this is the condition. Stationary standing waves are produced by superposition of two waves of the same frequency or amplitude traveling in opposite direction, right? So these are actually the conditions to form stationary or standing waves. Okay, so it means you may just simply write that the waves have same frequency, or you may also use to write same wavelength, or we may simply same period. So because once we know that the frequency is same, so time period will also be same. Okay, any confusion?
Okay. Nope.
Okay. And the last part is that state two waves in which a stationary waves differ from a progressive wave, that we already discussed in the start of this question. This question is related to progressive wave, and progressive and standing waves both are different from each other. So you need to write two difference between progressive and the standing wave. So any idea what will be the difference?
Stationary is like in one place, but progressive is moving.
Okay, nice. So one thing we write in our first point is that stationary waves, because this is a very common difference from the stationary.
And in the stationary wave, I think there's something to do with like the phases as well.
Yes, it may be like the same concept. So the first point that stationary wave does not propagate energy. If we are talking about the progressive wave, so progressive wave transfers energy.
Also, I think the progressive wave will have like the progressive one, it's moving, right? So that means
Yes.
it shouldn't have like nodes or antinodes, but then stationary ones should have.
That is the second difference. You now got the second point, that there is a difference of the node and anti-node concept, because in progressive wave we never discuss about this concept of node and anti-node.
Yeah.
So the first point is very simple. You may complete the statement by yourself because we got the concept. And the second one is that the stationary wave. Not, sorry, has not and and if we are talking about the progressive one, it's not have. Okay, so this is our complete question of 13 mark. Let's consider one more question. The questions of the waves are interesting if you got the concept right. So that will be something different from the other chapters. But if you are not getting the concept correct, so that will be very difficult one to solve the waves question.
Yeah.
Okay, one more question that is related to the same topic that we studied today. So in this concept, we are having a light from a laser. We also discussed that we use laser for the coherent concept, right? So laser is a coherent wave source. So that's why we are using laser from a laser is used to produce an interference pattern on a screen as shown in figure. So there are different values mentioned in the question. Let's start to mark the values. We mark the values like this. Yes. So D is the distance between slit and the screen. A is the distance between the center of the slits. And X is the distance between two consecutive crusts, right? So let's mark the points first. So this value will give you the concept of A, and this value gives you the concept of D, and this will gives you the concept of, let's suppose this is our first central bright fringe, and this is our consecutive or successive bright fringe. So this is equals to what? X. Okay. Any confusion?
Nope.
Okay. So these are the values that we already marked from the start of the question. Now let's move towards the question. In the question, they were talking about now state what is meant by coherent. So we already discussed the concept of coherent. What is the meaning of coherent? We studied today in coherent is, yes, if two waves have the same frequency and constant phase difference. So that is known as
Okay.
coherent, right? So you just need to write the same thing over here. So two sources are coherent if they have same frequency and phase difference, right? And the second part is for the two waves superposing at point R, calculate the difference in their path in nanometer from the slits, right? So they are talking about point R. So point R is over here, okay? So what we need to do, and what they are asking actually, for the two light waves superposing, okay, the difference in their path length in nanometer from the slits. Okay. So they are talking about point R. Any idea how to solve this part?
No, not really.
Okay, so what we need to do from in the diagram, we discussed that they are talking about the part difference actually. So we just need to draw, let's suppose from the first slit, this is the distance from the first slit, and this is the distance from the second slit. Okay, and we need to use the formula that we discussed in the part difference. So your part difference will be equal to n times lambda. So lambda is the value of the wavelength, the light of wavelength. This is equals to 660 nanometer. And if we consider, actually I write the formula for the bright fringe. If you remember that formula, yes, this there is the formula. For bright fringe, for the constructive interference, we use the formula of n lambda, right? But in diagram, you observe that it was written as the dark fringe, this one, right? So what we need to do, our first bright fringe will be over here. So after dark fringe, we are again getting the same bright fringe, right? So we simply use the formula of bright fringe. What we need to do, this is our first fringe. After this, at dark fringe, we are having dark fringe, right? Because after this half, we will getting the second wave, bright fringe. Okay. So if you are using the formula of bright fringe, so you may use the same concept 1.5. Otherwise, you may use the formula for dark fringe. Okay. You will get the same value. Because in dark fringe you have formula n is equals to 1 over 2, so that 1 over 2 automatically decrease your value by half. Okay, so we just simply use n is equals to 1.5 and lambda is 660 nanometer, means 10 to the power minus 9, and we need to find answer in nanometers, so just simply multiply 660 by 1.5 and rest of thing remains same. So what is the answer? So your final answer will be equal to 990 nanometer. Okay. Any
Not
confusion?
this. Nope.
Okay. The second part is their path difference. Okay. So now we need to find out their path difference. So for their path difference, let's see. Sorry, their phase difference. Yes, their phase difference. Okay. We discussed that for bright fringe, we just mark 1.5. And we know that if we consider complete degrees, so we started from 0, and if we complete our round, so we will get 360 degrees, right? So what actually we need to do over here, we just need to simply multiply 1.5 by 360, because we are at this specific point. And if we complete around 360, so we will get a complete degrees in radians, or if we are going to calculate in radians, or if we are going to calculate in degree, because they are asking in degree form. So we know that their path difference is equals to 1.5. So in their path difference, we got the concept of n is equals to 1.5. So we just need to simply multiply this n by 360. So you will get your final answer, that is equals to what? multiply by 360. Okay.
Okay.
And what is the answer? It is equals to 540 degrees, right?
Yeah.
Okay. And the next part is calculate the distance OQ. In the question, OQ is the first central bright fringe and Q is the first bright fringe. Actually, it is equals to X. Now you just simply need to use the formula of the young double slit experiment, this one, because we need to find what? X. Yes, X. So X is unknown actually. So we just simply need to use a formula, and formula is a simple one. We written over here what? Lambda is equals to AX over D. So it will be shifted like lambda D over A. So lambda D over A is equals to X. So you just need to substitute the values. All values are in your question. Lambda is over here. D is mentioned in the question. And A is also given in the question, right? So you may just simply solve by yourself. Okay. Any confusion?
No, it's good.
Okay. Part three is the intensity of the light incident on the double slit is increased without changing the frequency. So we are not going to change the frequency. The intensity is automatically increased, or maybe some factor we need to find out. Describe how the appearance of the fringes after this change is different from and similar to their appearance before the change. So actually, we are not going to change the frequency, right? Because we studied that in coherent, we need to have same frequency and same phase difference, right? Constant phase difference. So that's why they are asking if their intensity will increase. So describe how the appearance of the fringes after this change may be different, or maybe they will be similar as compared to their final stage in initial stage, right? So basically what happened, you know that if we increase the intensity of the light, so intensity means your brightness will increase. If we are using 60-watt bulb in our room and we replace it by 100-watt, so automatically the brightness of the lamp will increase, or the brightness of the room will automatically increase, right? So what actually happens in the first part, that your bright fringes will become more bright, right? Bright fringes will become brighter because already they are bright, and if we increase the intensity, so they will become more brighter. Okay. And what about the dark fringes? Any change?
There'll be no change. It just stays the same.
Yes, because they are already dark, so there will be no change. So no change in fringes. And the third point. Okay, so third point is related to the distance, right, or the spacing. So their spacing will remain same because there is
Okay.
change in the frequency. So no change in fringe spacing also. Okay. Any confusion?
No.
And this part is your homework. Try by yourself because that is related to your basic electromagnetic waves chapter.